Screen sharing working?
Yes.
Okay, so we are a little bit behind schedule, but should we start or?
Please start. Please start.
Okay. Okay, so welcome everybody to the Best Paper Award session. Me and Tom will be chairing it. Tom is on the chat window. Remember, you can ask questions during all talks by posting them on Zulip or on the Zoom chat, and Tom will bring them up at the end of the session. So as usual, as every year, Crypto recognizes some papers with an award. And this year, we selected as the Best Young Researcher Award recipient, the work by Joseph Jagger and Nirvan Tyagi, Handling Adaptive Compromise for Practical Encryption Schemes. So this work was already presented as the opening talk for the conference yesterday. If you missed the presentation, you can watch the recorded video. For the Best Paper Award, we selected not one, but three papers in three different areas of cryptography. In no particular order, the one award went to the work of Susan Hohenberger, Venkata Koppula, and Brent Waters for their work on chosen ciphertext security from injective trapdoor functions. Another award went to Wouter Kastrick, Jana Sotakova, and Frederick Vercatteren for their work on breaking the decisional Diffie-Hellman problem for class group actions using genus theory. And finally, an award went to Christoph Bjerl, Gregor Lander, and Josuke Tojo for their work on improved differential linear attacks with applications to ARCS ciphers. So without further ado, let's move to the first talk of the session. So I'll, how do we do this? I'll close my screen sharing so that we can get the first speaker.
Okay, can everyone see this okay?
Yes.
Okay. So I'm Brent Waters, and I'll be talking about chosen ciphertext security from trapdoor functions. This is joint work with Susan Hohenberger and Venkata Koppula. Before I begin, I just want to give you a thank you on behalf of all of us for the award. It's a great honor. I can't say I pictured giving such a talk from my office in Austin, Texas, but I guess you can't always predict how things will go in life. Okay, so I'd like to begin by reviewing a very fundamental building block of cryptography, which is public key encryption. A public key encryption system has three algorithms. The first is a setup algorithm, which takes as input a public key and a secret key, or sorry, outputs a public and secret key pair. Next, the encryption algorithm takes as input the public key and a message M, and outputs a ciphertext, which I'll denote as the highlighted version of M. And then finally, sorry, let me change something. And then finally, there's a decryption algorithm, which takes as input a secret key, the encrypted message, and outputs the message M. Now, when we first learn about public key encryption, the security notion we learn in our classes is usually security against what's called chosen plaintext attack. Roughly, an attacker gets to choose two messages, M0 and M1 of its choice, submits them to a challenger, and the challenger will randomly choose one of these two to encrypt and send back as a challenge ciphertext to an attacker. Now, we say a scheme is secure if an attacker's chance of guessing which one it is only a negligible amount better than 1/2. So while CPA security is being very foundational, there are limitations to it in that the only type of attacks we contemplate are ones when an attacker receives the ciphertext and simply just stares at it and tries to figure out what the message is. However, in real life, an attacker might have more tools at its disposal. For example, suppose Alice is sending an encryption of M to Bob, and we have an attacker in the middle who has no idea what M is because the scheme is CPA secure. However, it might be able to change, even without knowing M, it changes the ciphertext into a different one, which is an encryption of 2M, and perhaps learn something by Bob's reaction to seeing the ciphertext. Now, while this example here is sort of cartoonish, in real life, such attacks can manifest into serious attacks. One of the most prominent examples being the Bleikenbarker 98 attack on the SSL protocol. To that end, the communities developed a different definition of security, a stronger one, called security against chosen ciphertext attacks. This definition behaves similarly to CPA encryption in that there's a challenge ciphertext and the attacker's trying to figure out, is this an encryption of M1 or is it an encryption of M0 or is it an encryption of M1? But we're going to initially endow the attacker with a decryption oracle. And it can submit any ciphertext of its choice, except for that challenge ciphertext, to the decryption oracle and see what see what the output is. And CCA security is just is of very high importance, pretty much for any scheme that you would consider standardizing, anything you would consider deploying. It really has to be CCA secure to even be considered in the first place. Now, over time, the community has realized the importance of this, and a lot of work's gone into this over the last, let's say, 20 to 30 years. And I just want to point out a couple. I won't have time, obviously, to put out all the great works in CCA security, but I want to just put a couple here up on the slide. In the early 90s, we saw works that could combine CPA security with a very powerful primitive called non-interactive zero-knowledge proofs, and these can compile into CCA security. Next, in 98, a breakthrough result due to Kramer and Shoup showed how to get practical chosen ciphertext secure encryption from the decisional Diffie-Hellman problem. We also see how to get it if we happen to have identity-based encryption, we can get CCA security. Also work I was involved in with Chris Pikert showed how to get security from the learning with error assumption if we go through a intermediate primitive notion called lossy trapdoor functions. And then finally, we even seen how to get it from the learning parity with noise assumption. And I think in totality, I could say that over time, the community as a whole has become very, very good or very masterful at taking a particular number theoretic assumption, using the structure that seems to come with these things, and crafting a CCA scheme from this. What I want to focus on in this talk is to gain, let's say, an even deeper understanding, and how do we get chosen ciphertext security from more general, less structured assumptions. And in this talk, the focus is going to be doing it from a very old functionality called injective trapdoor functions. Now here, a trapdoor function, the way it behaves is that there'd be a setup algorithm which produces a public key K and a secret trapdoor TD. Now, given the public key K, anyone can evaluate this function f sub k on a random input x and get y. And this will, since it's injective, y will uniquely determine x. And there's also an inverse function where given y and the trapdoor, someone with the trapdoor can compute x. The security property that we want is that given the public key and the image y, it should be hard to invert it and compute x if x was chosen uniformly at random. Now, the most important feature, I think, of trapdoor functions, at least for this talk, is that the trapdoor or the sort of decrypt or invert algorithm recovers all the input. When you're evaluating this function, x is the only input, the entirety of the input to the function. We can contrast this to the encryption algorithm of an encryption scheme. So in an encryption algorithm, the public key and the message are inputs, but there's also a hidden input here, which are the random coins used to encrypt that I didn't show here. And when we decrypt a ciphertext with message M encrypted under R, we will be guaranteed to recover M, but there's no guarantees at all about recovering R. The randomness could simply be lost. Okay, so the one reason to study CCA security from trapdoor functions is that there's a very long history between the two. First of all, we could get CPA security from trapdoor functions due to Yao. The famous Fugisaki-Okamoto transform showed how to get CPA security from CCA security if we use the random oracle model. However, one interesting fact along the way is that they essentially construct a trapdoor function implicitly in order to do their transformation. Also, we have Noor-Young and Dolev, Dwork, and Noor showing how to get CCA for enhanced or maybe double enhanced trapdoor permutations. The work of Chris Pikert and myself and Rosen and Segev showed how to get CCA security from lossy trapdoor functions or the generalization of correlated input secure trapdoor functions. And what I want to ask here is, so it seems we can do CCA security from some type of trapdoor functions, if we add the right adjective or kind of endow them with enough power, I want to ask here, can we do something much more basic? Can we get them from just any old injective trapdoor functions? Can we just do it from, plainly from that? And the answer is indeed yes. That's what the result of this paper is without any caveats. We go from trapdoor functions to CCA security. Quick one-slide overview of how we do things is that we're first going to introduce an intermediate primitive, which will be public key encryption with randomness recovery, something new that we call, and we show how trapdoor functions implies this. The reason we do this is that it's much easier to show our construction using this intermediate primitive here. And then we show how to go from this to CCA security. There's a couple helper primitives on the way. One is a digital signature scheme, and the other one is something we'll call tag set commitments. These can both be realized from public key encryption with randomness recovery. So there's really only one assumption feeding into this whole thing. Okay, so let me first introduce this CPA with randomness recovery primitive. It's essentially public key encryption, but with two different features. The first one is that the decryption algorithm, if a ciphertext is an encryption of M with randomness R, the decryption algorithm will actually recover both M and R. So it has that type of trapdoor flavor to it, where it actually tells you what the randomness is. The second one is, in addition to the decryption algorithm, which decrypts with a secret key, we're going to sort of give an alternative way to decrypt, where if you happen to have the randomness R that was used for ciphertext, you can actually use this, what we call recover algorithm, and get the message M using just that. Okay, so we can decrypt the secret key, or if we happen to have somehow known the randomness. Now, it turns out that, as I said, trapdoor functions imply CPA with randomness recovery. The transformation is actually pretty simple. The public key and secret key for the randomness recovery scheme is just the public key and secret key for the trapdoor function. To encrypt, we choose a random X. You evaluate f of X and give that as part of the ciphertext. And then to encrypt a bit message, you take the hardcore bit of X and XOR it with M. And then likewise to decrypt, I just run the trapdoor function, or run the inversion function on Y and get what X is, take the hardcore bit of X again, and I can XOR that out and get the message M. And the recover algorithm just has X to begin with, in a sense, so it can just take the hardcore bit of it and XOR it out. Okay, so this gives you a scheme for 1-bit messages for CPA with randomness recovery. If we want to get many bits, we can just simply concatenate a lot of these, together. Okay, for that reason, since we now have this new primitive and can see that it's implied by trapdoor functions, we're just going to set trapdoor functions aside for the rest of the talk almost, and just go from CPA plus randomness recovery to CCA, to chosen ciphertext security. Okay, so here's a 10,000 overview of how I'm going to do things. First of all, our construction will, a chosen ciphertext secure ciphertext in our construction will have many little different CPA with randomness recovery encryptions comprising it. We're going to essentially encrypt the message many different times, but we're going to have a tiny bit of redundancy. And for each of these little encryptions, they're not going to be made completely at random. There's going to be a little bit of redundancy in them. But we have to be careful. We'll see, we have to be pretty careful of this redundancy. If we made it too redundant, and we'll see what I mean by this in a second, we might even kind of go the opposite direction and go from a CPA secure scheme to one which we can't prove CPA security. So we need a tiny bit of redundancy to maintain CPA security. And the reason we'll have this redundancy is it helps us answering decryption queries. So for the remainder of the talk, I'm going to really do two things. First, I'm going to show a simplified version of the construction, kind of show where the redundancy plays in here, and argue why it doesn't hurt CPA security. And then next, I'm going to show how to add a little bit to it so that we can make it a little more complicated, so that we can actually handle decryption queries, which will give us the chosen ciphertext secure scheme. Okay, so here's our, let's say, our simplified construction. So to create the public and secret keys, I'm going to run the setup algorithm of the CPA with randomness recovery scheme 2 times n times. So I'm going to come up with my public key is going to consist of 2 times n keys, which I'll just denote with a double subscript over here. Next, and we'll have the corresponding secret keys. Next to encrypt, what I'm going to do is I'm going to pick a random set S of size n. So essentially, I'm going to pick half of these slots. There's 2 times n slots. I'm going to pick half of them, and let's say highlight these in yellow. The ones that aren't highlighted, I'm just going to encrypt a special, let's say, don't look here symbol pound. And in the rest of them, what I'm going to do is I'm going to encrypt the message over and over again. So I encrypt in the first slot the message M under randomness R1, the second slot the message under randomness R2, and so on and so forth. And these are going to almost be chosen uniformly at random, except I'm going to restrict it such that the random coins here all XOR to 0. And looking ahead a little bit, if the coins always XOR to 0, this means you can actually learn any one of them from n minus 1 of them. Right? So this is the tiny bit of redundancy I was talking about. Okay, so we'll have, so the yellow ones are the correlated ones, encrypting M, and the gray, little gray boxes are ones just independently encrypted with the special pound sign. Okay, so the first thing I need to answer is, did I even make things worse? Is this scheme CPA secure? Not immediately clear because I had this correlation of the randomness. Okay, so here's how we're going to do it. What you might first think I would do is I would take all these M's and try to change them to pound symbols, but I can't immediately do this actually because of this redundancy or this correlation and the randomness that I have. So somewhat counterintuitively, I'm going to actually give more information about M. I'm going to give it even more times in the challenge ciphertext to prove security. So first I can add M everywhere, and that should just follow from CPA security. That's no big deal. And then second, I want to actually argue that statistically, the correlation isn't even there. Just kind of magically, we can get rid of the yellowness and just assume that all these were encrypted uniformly at random. Okay, so why could I possibly do this? Let me give you an intuitive argument why this is true, just assuming that n is equal to 4 in this slide for fun. Okay, so I want to argue that the distribution on the left, or on my left, is indistinguishable from the distribution on the right, where everything's chosen just uniformly at random. And on the left, these yellow things will XOR to 0. Okay, so suppose that L was the length of the random coin. So each of these strings R sub something will be of L bits. And let's say lambda is our security parameter. We're going to set capital N equal to L plus lambda. Now we expect the numbers, so there's about roughly 2 to the n subsets of size n. And each one of these has a 1 over 2 to the L chance of XORing to 0. So even if we chose everything uniformly at random, we will actually have an exponential number of things that happen, just in some sense accidentally, to XOR to 0. And intuitively, the argument here, let me bring that back up here. Intuitively, the argument here is that since there's an exponential number already, actually just programming in 1 shouldn't be statistically noticeable. I'll mention that the actual proof in the paper is more rigorous than that, of course. We show this under the leftover hash lemma, but just intuitively you can think, well, if I have an exponential 2 to the lambda number of things, just programming in 1 more shouldn't be statistically very significant. Okay, and then once we happen to have that step, well, now we have everything under uncorrelated randomness. So what we can just do is do the normal CPA scheme and change everything to bot, and or change everything to the pound sign, and then all information about M is gone. Okay, so the good news is so far we have not made things worse. So what about, is it actually CCA secure? Can we handle decryption queries? To do so, the way we're going to go about this is intuitively when going from the pound sign to adding in these M's, we're going to do them in the normal hybrid way where we add in 1 M at a time. We change 1 pound sign to an M 1 at a time. And so to do this for the CPA security experiment, we need to not know, at least in any point of this hybrid, we're going to not know one of these secret keys. At the same time, the trick is, while we're not knowing one of these secret keys, we're going to be asked to answer decryption queries. The reduction algorithm will have to answer decryption queries. So what we really want is we want a decryption procedure where the normal decryption procedure uses all 2 times n keys, but there's also a decryption procedure using all but one of the keys, 2 to the n minus 1 keys, which can decrypt in the same way, essentially the same way as the normal decryption procedure. So in the simplified scheme, we actually don't have this. It won't be CCA secure, but I'm going to add just a little bit to this to make it work out. To do this, I'm going to first introduce what I'm going to call a tag set commitment scheme. Here we're going to imagine that there's a universe of indices from 1 to 2 times n, and we're going to want a user to be able to commit to n sets of size n. So the first thing is there'll be a trusted setup algorithm, which I'll put some public parameters. Next, there'll be a commitment algorithm, which takes a set S of size n, and also some extra information, which I'll call a tag T. And I will output a commitment com, as well as sort of proofs of n separate proofs of opening, 1 for each item in S, 1 for each index in S. And finally, there's a verification algorithm, which will take as input a tag, the index, the proof sigma sub I, and the commitment, and output 0, 1. The correctness property is roughly what you would think it would be. If it comes out a commitment, then it should verify in the natural way. In addition, though, to this normal setup algorithm, we're also, in the spirit of equivocal commitments, we're going to have an equivocal mode, which outputs public parameter star, commitment star. And actually, what this does is it essentially says if you call setup on a tag star, it essentially allows you to cheat. Allows someone who create the setup to cheat, but only on tag star, and all the other tags it shouldn't. So it gives you 2 times n, more than you should, twice as many as you would normally have, of these sigma values. Now the security parameter that the security property that we're going to want in this scheme is twofold. First, as I said, even if we did equivocal mode for tag star, it should be hard to generate n plus 1 valid openings for any tag not equal to tag star. The second property is that it should be hard for anyone to distinguish between the equivocal mode parameters and the honestly generated parameters, assuming they're giving the sigma values just for one set S of size n. So you can't tell between these two. And I won't have time to go into how we build this today, but I'll just denote this can be constructed from pseudorandom generators and sort of a similar spirit to the Norbit commitment scheme and other things we've seen before. Okay, so let's see, now let's see the construction in totality. Okay, so the public and secret keys, public key scheme, setup is almost as before, except for we're going to have the add the public parameters for the tag commitment scheme. For the ciphertext, we're still going to choose the set S of size n, just like before, except for we're going to do something a little bit more here. The first thing we're going to do is generate a verification and a signing key for a signatures scheme. And then we're going to call this commitment scheme for set S that we chose, and with the verification key equal to the tag. It's kind of a common thing to do. And then you'll get as output a commitment and these n sigma sub I values. Now, when we encrypt, instead of just encrypting m everywhere, we're going to encrypt m and the corresponding sigma value. So here I'll encrypt m and sigma 1 under randomness R1, and so on and so forth to m and sigma sub n for the nth index I chose under randomness R sub n. Again, we're going to have this redundancy where all the values, the RI values, XOR to 0. And that's it. It's actually not that complicated of a construction. Okay, and then the ciphertext consists of the verification key, the commitment, and a signature on everything that came into there. Okay, so now we need to see how decryption works. I'm first going to tell you a way to decrypt using all 2 n keys. Then I'll tell you a way to decrypt using 2 n minus 1 keys. I'll try to roughly argue that these are equivalent. The decryption procedure will essentially perform a bunch of checks. If any one of them fails, it says, get out of here, I'm going to reject this ciphertext. Otherwise, it will tell you the message. First thing it does is it verifies the signature. If that doesn't work, reject. Next, it's going to use all 2 times n of its keys and try to decrypt each one of these positions. And it's going to make a list or a set U of all the indices where decryption worked and where the corresponding indice verified according to the commitment scheme. So it should collect a set U, and the set U should be of size n. Okay, so intuitively, the set U should be all these yellow values for a well-formed ciphertext. And if it's not a size n, reject also. And finally, we're going to check that the randomness XORs to 0. And then we want to make sure that these yellow or claimed yellow ciphertexts were actually created correctly. And we're going to do this procedure of the decryption algorithm calling encryption again. It's going to it's going to call the encryption algorithm with the randomness recovered and make sure that it's what it was originally to make sure things are kosher. Okay, so now let's see a method for decrypting using all but one of the keys. I'm going to just imagine this key in the top left that I scratched out here is gone. Okay, so to decrypt, we're going to verify the signature again. That makes sense. We're going to decrypt using all 2 to the n-1 keys that we have, okay, and make this list U in the same way. But it's possible at the end, the size of U is n-1, and it's possible that the missing value is just the secret key that we don't have. And it at first seemed like, okay, we're in trouble here. We don't have the secret key. We can't decrypt. But remember, in a well-formed ciphertext, all these RI values XOR to 0, which means we actually know what R1 is, or what at least it should be, by just XORing all these RI values that we were able to recover. So what we can do is we can come up with R1, use the recover, this alternate recovery decryption mechanism to decrypt, add it to the set U. Now, at this point, set U should be of size n. Whether or not we added something to it, we can check that. And we can perform the same re-encryption checks that the normal one did. Okay, so I won't have time to go to actually prove that these two. So what we now need to do is prove that these two indeed do the same thing. In the paper, it's essentially a case analysis with 3 or 4 cases. I won't have time in this talk to go through each of them, but let me just pull out one example here to show you at least how the redundancy works. Okay, so let's imagine we actually have a well-formed ciphertext that was decrypted correctly where things XOR to 0. If we decrypt using the 2n key method, the signature of verify will collect all 4 of these yellow values, they will XOR to 0, and all the re-encryption checks will pass. So things go okay, and the algorithm outputs M. If we only have 2 to the n-1 keys, that means 1 secret key is missing. We recover 3, the right 3 yellow values, and then we can figure out R1 is equal to the XOR of the rest of them, and then we can recover the 4th by just using this recover algorithm. And again, all checks will verify and re-encryption checks will pass. So this is this balance between how we can decrypt using just one, with missing just only one secret key. Okay, oops, okay. Now, that was just one ciphertext. What we claim is that in all types of ciphertext, essentially, the behavior is indistinguishable. And this includes maliciously generated ciphertext, and that's where using things like the signature and the tag commitment come in. I won't have time to show this today, but it is in the paper. Okay, now once we have all these kind of concepts in place, what we have is that we can have a hybrid proof. I won't have time to go through it. Essentially, the hybrid is reject any queries which the verification key is the same as the challenge ciphertext. Then we're going to change these pound symbols to M1 by 1, as I denoted. We're going to use the ability to decrypt with 2 n-1 keys, then take away the redundancy like we saw, and then change everything to pound 1 by 1. Okay? Okay, so this essentially concludes my argument of the CCA, and I'd like to take just a minute or two left that I have to do a little bit of a retrospective on the ideas from this work. Again, we go from trapdoor functions to CCA security. And one interesting open problem is, can we build, now that sort of the box is open, can we build other primitives from just trapdoor functions that maybe we didn't think we could before? The second point that's important here is that there's a very fine balance between the amount of redundancy that we had, too much and it's not CPA secure, and if we had none at all, then we wouldn't be able to answer these decryption queries. So for some perspective, on the far left here, if we didn't have any redundancy, we couldn't improve CCA security. We couldn't answer these decryption attacks. We had just a tiny bit, which is somewhere on the spectrum. And we can look at some other previous work, like the law CTDF or correlated products, as having a lot. but the consequence was that they needed a souped up version of trapdoor functions or CPA with hinting PRGs. And then I'll just conclude by saying a very clear open problem is we went from trapdoor functions to CCA security. Can we go from CPA security to CCA? I don't know. It's hard to say. It seems to give a little no hope. Of course, we do use a lot of the power of the trapdoor functions. Okay, thank you very much.
Okay, thank you, Brent, for the great talk, the great work.
Thanks.
Oh yeah, so we can do one big clap to all our winners at the very end. So in the interest of time, perhaps we have time for one question or comment, Tom. And
sure. Yeah, so we have one question on Zulip from Dan Bernstein. So injective trapdoor function, this talk sounds like perfectly correct deterministic PKE in, for example, HHK17. Which raises, well, 3 questions. We'll start with one and we'll see how far.
Sorry, it sounds like what? I'm sorry?
HHK17. Can you hear me?
Mm-hmm. Okay, perfectly correct. Okay.
Yeah, and perfectly correct deterministic PKE. Okay. So can the technique here work with decryption failures is the first question.
Oh, okay, if the scheme was not perfectly correct. So yes and no. So we need it to be what's called almost all keys correct. Which means that with all but negligible probability, it will be perfectly correct. But if it happened to have if there happened to be a significant chance that there could be correctness failures, the proof actually cannot go through. It's a little nuanced. I can nuance that a little bit, but that's a good question. And the answer is no, we do need perfect correctness. And it would be interesting to show it from non-perfect correctness, let's say.
Okay, great. So one more quick question. It's from Daniel Brown. Impossibility results about provable security for RSA OAP are known. So I wonder if this result has been double-checked against the state-of-the-art impossibility results.
Impossibility results for
RSA OAP.
So you're saying for particular trapdoor functions that there's the RSA OAP impossibility? Right. So I would. Okay, we didn't explicitly check it against this, although I will say the RSA OEP is a particular transformation. For example, it doesn't use the RSA trapdoor function. It doesn't use 2 times n keys. So it's a different transformation than this one. So to the best of my knowledge, the impossibility result is for that particular transformation, which wouldn't necessarily rule out other transformations.
Right, yeah, I think that's correct. Okay, so I think in the interest of time, there are some more questions on Zulip, so maybe you can answer them there with chat.
What Zulip is? Okay, good.
Yeah.
Yeah, so there's no link to Zulip next to the best paper session on the web page, but any other link to chat work. Anybody interested in asking questions or discussing further can go to Zulip and post their questions there. And so now let's move to the second talk, and Wouter will give the talk. So please, unmute and start sharing your slides.
Okay, is this visible?
Looks great. Yeah.
Okay, so yeah, first of all, thanks also from the 3 of us for handing over this award, which is really an honor. So our paper is on breaking the decisional Diffie-Hellman problem for class group actions using genus theory. And when I say we, I mean joint work with Jana Sotakova from Amsterdam and Frederik Verkouteren from KU Leuven. And so let's first focus on this decisional Diffie-Hellman problem part. So let's formulate this for the classical Diffie-Hellman key exchange protocol in the way it was introduced in 1976 by Diffie and Hellman. So there, Alice and Bob agree on some finite prime field, Fp, and they fix a generator of the multiplicative group, G, and then Alice chooses some secret exponent A, computes G to the A, sends the result to Bob. Bob does the same, chooses a secret B, computes G to the B, sends the result to Alice, and now both parties can compute the common secret G to the A, B. So an eavesdropper listening to this channel sees G to the A, sees G to the B, and ideally spoken, G to the AB to her just looks like something absolutely random. Okay, and so this ideal is formalized in the decisional Diffie-Hellman problem. So it's presented as a game, really. So the attacker is presented samples from one of two distributions. So either he's presented samples, really genuine Diffie-Hellman samples, so the form G, G to the A, G to the B, and G to the A, B, or he's really presented random samples. And so he has to be able to tell from which distribution he gets the samples. And if he can win this game with a non-negligible advantage, he breaks the decisional Diffie-Hellman problem. And this is like a key hardness assumption and all sorts of provable security proofs. Now, for the original Diffie-Hellman proposal, this is not hard because of the following property. G to the AB, this element of FP, will be a square if and only if G to the A is a square or G to the B is a square. So we have this equivalence, and this can be tested efficiently thanks to the Legendre symbol. So an attacker just computes these three Legendre symbols and verifies whether this equivalence holds. And if it does, and if it keeps doing so, then very likely we are in this first case. And as soon as it doesn't, we are definitely in the second case. Okay. So this is like our motivating example for this work. Just let me remark that, of course, in practice, for the way we do Diffie-Hellman nowadays, this is not a problem. Because in practice, like also to avoid Pauli-Hellman type reductions, we work in a prime order subgroup of FP star, and then automatically all the elements we work with are squares, and so this is no longer useful as an attack. Okay, so we are trying to do the same for a variant of the Diffie-Hellman key exchange protocol that was proposed by Couvegnier in 1997 and then rediscovered by Rostovtsev and Stolbunov in 2004, and so now goes under the name CRS. And also Seaside falls within this framework. So the exact terminology is not too important for now, but it works with a group action. The group acting is an ideal class group of some imaginary quadratic order O, and the set on which this group acts is a set of elliptic curves over some finite field FQ, and the action is through isogenies. That's what's written here. But the layout is really the same as in the classical Diffie-Hellman protocol. So Alice chooses a secret ideal class A, acts on this starting elliptic curve E with it, and the result AE is sent to Bob. Bob does the same with the secret ideal class B, and then both parties can compute the action of AB on E. Okay, and so we are interested in this because it defies Shor's algorithm, so it's possibly post-quantum secure. In any case, an eavesdropper sees E, sees A, E, sees B, E, and so the same question can be asked: is A, B, E something genuinely random to her appearance or not? Okay, and so we can formalize this in a non-surprising way as follows. So this was first appeared formally in Stolbunov's PhD thesis. So the idea is now, or the game is now, to distinguish between the distributions where on the one hand you get genuine Diffie-Hellman samples, so E, A, E, B, E, A, B, E, or random quadruples, okay? And so our main contribution is that we break this for almost all instances of the class group. I will say something about this almost all in a second. By providing a family of distinguishers, and you should really think of these distinguishers as something similar to the Legendre symbol for classical DTH, okay? But again, as in the case of classical DTH, it's easy to fix, either by working with a subgroup of the class group or by working with one of these few class groups to which the attack doesn't apply. Let me already mention, for instance, the group that is used in Seaside escapes from this attack, okay? Now, let's give a slightly more precise statement. And so this involves group homomorphisms that are called assigned characters. So this is terminology that comes from genus theory. This is in our title. But an assigned character for now is just a group homomorphism from this class group to the group with two elements. And so what we can do is, given such a group homomorphism, and given a pair of elliptic curves, E and E prime, that are connected by a secret ideal class A, we can evaluate this assigned character in this A without knowing A. So A is really unknown. We are just given these elliptic curves. Nevertheless, we can compute this. And let's say quickly. Okay, so this modulus of the character is something that will also be apparent soon what it is. But let's say in the cases that we run this attack, this will be very small, and so this will be an efficient attack. So why is it an attack? And I should mention that this is really classical time, so there's no quantum steps involved. Why is this an attack? Well, this distinguishes between Diffie-Hellman quadruples and random quadruples because this is a group homomorphism. Okay, so using this algorithm, we can compute chi of AB, we can compute chi of A, we can compute chi of B, and so because it's a group homomorphism, this relation should hold always. Whereas for random quadruples, this will only hold with probability 1/2. And so very quickly, this can be used to distinguish these two distributions. There's one caveat here. There exist assigned characters that are trivial, that constantly take the value 1, and then in that case, this is not true. Okay, so as soon as chi is non-trivial, but I'll also say something about that on the next slide. Let's first describe these assigned characters in more detail. And so this builds on a very old observation due to Legendre, essentially, of course, using a different language. So we have our imaginary quadratic order O, as I said, and we consider its discriminant. So this is an important integer one can attach to that. And then for all odd prime divisors of that discriminant, we have the following phenomenon. So if we take a non-zero ideal I of our order O, and we consider this Legendre symbol, so this is the norm of the ideal over our prime M, yeah, then this only depends on the ideal class of I. So if we take an equivalent ideal and compute this expression, we will always get the same thing. So this is constant on ideal classes. That's the observation by Legendre. There's a technical assumption here, but this is really nothing. So one needs that the norm is co-prime with the discriminant, but every ideal class contains such ideals, so that's not a restriction. So in other words, we can define a well-defined group homomorphism from this class group to this group with two elements, sending an ideal class I to the Legendre symbol of the norm over M. Okay, and this is really a group homomorphism because both the norm and the Legendre symbol are multiplicative. Okay, and so this is our first example of an assigned character. Just for the sake of completeness, there are also assigned characters attached to the prime 2 dividing the discriminant in case this discriminant is even, but it's a bit more technical, so I just give the descriptions here, but the only thing you should remember is that they are also very explicit and also taking the norm as an argument. Okay, so there's a table which you can use to check which of these characters are well defined, but I won't go into that. Now, an interesting statement from genus theory. So genus theory was kind of wrapped up by Gauss, building on this work of Legendre in 1801. So the number of assigned characters, so the number of such characters is related to the size of the two-torsion part of the class group in this manner. And a corollary to this is that at most one of these assigned characters is trivial. And so I mentioned that it's possible that an assigned character is trivial, but actually this is true for at most one of them. And so in particular, so this M is of course this modulus from the previous slide. We are guaranteed that the second smallest prime dividing the discriminant, in the worst case, we have to go to the second smallest prime dividing discriminant to have a non-trivial character. Okay, so that's not too bad. If R is 1, if there's only one assigned character, and you see from this that this is equivalent to saying that the class group has an odd number of elements, then there's only one assigned character and then it is trivial. So that's bad news. And this is exactly the situation in C-side. Okay. Now, how does this attack work? Well, to understand the attack, we need a few more things about this class group action, but actually not too much. So just let me recall that this set on which we are acting is a set of elliptic curves over some finite field. And all the endomorphism rings, but we won't really need that, are isomorphic to this imaginary quadratic order that we fix, and we also fix the tricks, but we actually also won't need that. The most important ingredient on this slide is this sentence. So whenever we have an elliptic curve in this set, and whenever we have an invertible ideal in our imaginary quadratic order, well, to this we can attach an isogeny emanating from this elliptic curve E. The codomain lands again in the same set. And the two most important features of that isogeny for our needs are that this isogeny is defined over FQ, and the degree of the isogeny is the norm of this ideal. So that will really be used later on. And another nice feature, but okay, this is just for completeness, is that this codomain only depends on the ideal class of the ideal. Yeah, and that's actually what gives rise to this action. And so you can really act on an elliptic curve with an ideal class, and you always end up with the same elliptic curve E prime. And so this turns out to be a free and transitive group action. So this is just a visualization. This is the set. We have our elliptic curve or any elliptic curve in the set, and we act on it with ideal classes. And as such, we walk around this set. Okay, now what is the strategy in some more detail? Well, remember, we want to evaluate an assigned character on a secret ideal class only being given two elliptic curves that are connected by that ideal class, okay? And remember, this assigned character, we will only discuss the ones corresponding to odd prime divisors of the discriminant because they are a bit easier. Remember that this is computed by the Legendre symbol of the norm over M, but we don't know the secret ideal class I, so we don't know this norm. What do we do know? Well, we know that these two elliptic curves are connected by an FQ isogeny of degree that norm. Okay, and we can also assume, as I already said, that that norm is co-prime with the discriminant. Okay. Now, what is then the idea or the basic strategy of our eavesdropper Eve? Well, the goal is to extract information about this norm modulo M using the Tate pairing. So the Tate pairing is a well-studied bilinear map taking values in two different groups. So one group is the rational M torsion of your elliptic curve, and the other is the set of rational points modulo M on your elliptic curve. And it takes values in the mth roots of unity. Okay, and the nice or the most attractive property for our needs is this compatibility property, which says the following: if you feed 2 points to the Tate pairing, or if you feed the images of those points under some isogeny to the Tate pairing, then the two outcomes are related by raising to the power the degree of the isogeny. Okay, now remember, the degree of our isogeny is precisely the norm of our ideal we are looking for. Yeah, so that's our hope, to be able, by computing some discrete logarithm, to extract the norm modulo M. That's the best we can hope, because we land in the mth roots of unity from such an equation. Okay, now it's not clear that this strategy will work, so let's discuss this a bit further. First of all, this assumes that the mth roots of unity are really contained in FQ star. And so that's not always true. And so potentially we need to extend the base field to achieve that. That's typically not a problem, except in the super singular case, there's a subtlety, because this can change the endomorphism ring and this can change everything. But in the ordinary case, this is fine. So that's not a big deal. Then secondly, we don't want this equation to be 1 equals 1 to the power the norm, because then we cannot learn anything. So we want this really to be a primitive mth root of unity. And then thirdly, and more importantly, or more challenging, is we want to have a pair of matching points. So because we don't know phi, we can't really compute phi of P or phi of Q for certain points P and Q. Nevertheless, this strategy seems to require a set of matching point pairs, PQ on the starting curve and P prime Q prime on the ending curve that are related through this isogeny. But here's an important relaxation. Actually, we don't need to have such an exact matching pair of points. It suffices that these points P prime and Q prime are the images up to some scalar, up to the same scalar. Why is that? Well, if we then plug these points inside the Tate pairing, because of the bilinearity, this lambda comes out to the power 2 as a square. And so this is enough, because we are only interested in the norm of our ideal, in the Legendre symbol of the norm of our ideal over M. And so this doesn't change if we scale it by a square. Okay, so that's really a crucial relaxation, and that's what will be possible. So here's a basic example to which this strategy applies. Assume that the M primary part, so what is this M primary part? It's a set of points whose order is a power of M. So this forms a group. Assume that this is isomorphic to Z mod M. So basically as small as it can possibly be, unless it's trivial. Okay, so we assume this, then automatically this is also true for our curve E prime. And that's because of the type of isogeny that connects them and forces the group structures to be the same. Okay, so we have this. And now as our point P, we just take any point here of order M. This exists because of this group structure. And here we take any point P prime of order M. Okay, so far we don't seem to have done anything interesting, but now note this secret isogeny phi is defined over FQ, and the degree is co-prime with the discriminant. So in particular, the degree is co-prime with M. So necessarily phi of P is a point on this curve of order m. And so because of this group structure, it has to be a multiple of p prime, or the other way around. P prime has to be a multiple of this phi of p. Okay, so we have this multiple, but we don't know which multiple. Now, the nice thing about this situation, as I will explain in a second, that for q, our second point, we can just take p again. Yeah, and then for q prime, we just take p prime again. And obviously, q prime is just lambda times phi of q, because q prime is p prime and q is p. Okay, and so we can indeed recover lambda squared times the norm from computing the state pairing because of the equalities that I just mentioned on the previous slide, by computing a discrete log. Remember, for this to work, we need that this is a primitive M-truth of unity, so it shouldn't be 1. But that's true by the non-degeneracy of the state pairing, but this strongly relies on this group structure. Okay, so I won't go into the details of that, but that's another point where we really use this group structure, that this is different from one. Now, this basic example generalizes to a slightly larger class of examples. I will go quickly over that, but if your M primary part is cyclic, then you can really play the same game. Again, for P and P prime, you take any point of order M, and for the same reason, they will be connected by a secret scalar lambda. But now for Q, you cannot take P, otherwise this state pairing would become 1. For Q, you have to take a point such that m to the r minus 1 times Q equals P. So something really at the bottom here of this tower. Sorry? Sorry, I'm...
sorry, I muted them.
Okay, sorry.
Just an interference, sorry.
Yeah, and so if we take our points Q and Q prime consistently like that, then this point Q and Q prime and Q and phi of Q are again connected by the same scalar lambda. Actually, it could only be that scalar modulo m, but that's enough for this, okay? And then you have exactly the same reasoning. So by taking Q and Q prime like that, you will have again an outcome that is different from one. Okay, now what about the general strategy? Well, then we use isogeny volcanoes. So what are isogeny volcanoes? Well, they are graphs whose vertices are elliptic curves and the edges are M isogenies. Okay, and so it's well known since work of Lenstra from '96, and this was also revisited by Miret et al. In 2007, that by walking down to the floor of the isogeny volcano, you can make the M primary part cyclic. For instance, here's an example where the M primary part is not cyclic. So this elliptic curve sits somewhere on this volcano, and now we walk down the volcano, and for each step, basically you will take a component here and take it and put it there. Yeah, so this will happen at this step, and then if we are at the floor, we will have a cyclic M primary part. So if we do this for our two elliptic curves together, we walk down all the way to the bottom. And now we know by this previous remark that these M primary parts will be cyclic. On the other hand, they will still be connected by some ideal in some class group. It will be a different class group because these descending isogenies change the endomorphism ring. Okay, but nevertheless, they will still be connected by an ideal. And by our previous work, we know how to compute, this character value of that ideal. Note, the order changes, but M will still be a divisor of its discriminant, so we'll still have that character available. And then we can prove, using a result in a paper, we found in a paper by Sutherland, that this character value that we computed is actually also the character value. Okay, so that's the complete story actually of our attack. So let me end with some concluding remarks. So I didn't say something about these characters epsilon delta that correspond to the divisor m equals 2, but actually the same strategy works. It's just a little bit more technical. Instead of the 2 Tate pairing, you need to work with the 4 Tate pairing or the 8 Tate pairing, but apart from that, there's no difference. I also kind of skipped supersingular elliptic curves. So I already mentioned it. If you extend the base field supersingular elliptic curves behave a bit more different, but also with respect to these isogeny volcanoes, they behave differently. But we can give a complete ad hoc treatment of the supersingular case. And actually, this was the first case that we did before doing the previous work. So let me just go quick over this. There are two interesting cases. So we always work with supersingular elliptic curves over Fp in this context, and either P is 1 mod 4. And in those cases, there's a unique non-trivial character. And there's a very explicit formula for evaluating the character in a secret ideal class connecting two elliptic curves. You just take the right curve coefficients and raise them, take the quotient and raise to the power p minus 1 over 4. Okay, so that's a very explicit formula. So here the attack also works. And if p is 3 mod 4, then there are no non-trivial characters. I already mentioned that. And this is, for instance, the case for C-side. And as a second remark, to break the decisional Diffie-Hellman problem, it suffices to evaluate one of these characters. But in many cases, you can evaluate several of these characters, or even all of them. And that's helpful because this will make your attack more powerful. Okay, so for each sample, you will have a bigger probability of being able to attack the decisional Diffie-Hellman problem. And actually, if you really can compute all the characters, what you're actually computing, this is also a consequence of genus theory, is the coset modulo the subgroup of squares inside the class group of your secret ideal I. Yeah, this can be used to reduce this to the hardness of the class group of the CRS protocol for this class group to that of the subgroup of squares. Okay, so let me maybe, yeah, just mention that the index, so the amount of reduction you have here depends on the number of characters, and as I already mentioned, this depends on the size of the two torsion part of the class group. So in a way, you could view this as a confirmation that the structure of the class group really affects the security of CRS. So I think I'm a bit over time. So let me maybe just mention with this recommendation that in order to avoid these kind of attacks, we recommend to use maximal orders because of a similar reasoning that was known before, and such that the class number is odd. And this is an example of such things. So I'll stop here. Thank you.
Okay, thanks a lot, Wouter, for your talk and great work. And so, Tom, we have time for a question, if any, or we can move to the next.
Sure. Yeah, we have a couple questions on Zulip. The first is from Tomas Rosa. It says, do you see some notable backward implications for complexity of certain instances of the hidden shift problem?
Well, except the last thing that I mentioned. But, so our attack computes the coset of the secret ideal class I modulo the subgroup of squares. And so this can be used to reduce the hardness of the hidden shift problem in this context to this smaller group, which is the subgroup of squares. Okay, but typically this is not a big reduction, but it could be at some power of 2, yeah, but some small power of 2. So that's the only thing we are aware of.
Great. And then one more question from Hotek Wee. Does the attack also work for D-Lin? The context being that DDH is broken in symmetric pairing groups. One way to get around that is to work with D-Lin.
I don't know what D-Lin is, I'm sorry.
Decision linear. Hotek, you can give more clarification if you like.
Sorry, I will need to look it up and
okay,
try to.
That's fine. We can take that to Zulip. I guess I just had a quick question. You mentioned that certain candidates like CSIDH, I guess, avoided this attack. Was that purposeful by the authors of the prior thing, or you think it was by accident?
This is by accident, yeah. Yeah. This was just because this happens to be the endomorphism ring of the easiest supersingular elliptic curve one can write down, which is y² = x³ + x. and so it's by accident, I would say. Yeah.
Great. Okay, so thank you very much. I think we can move on.
Okay, cool. So thanks, and time to move to the last talk, and best paper award winner, Yosuke will give the talk.
So can you see it?
Yes.
Okay. Okay, so thank you very much for introductions, and I'm very happy to get best paper award Crypto 2020. So I'm very happy. So the topic is about symmetric key crypto, and so it's a crypto analysis papers. So first 6 slides, so that I want to explain the high-level overview for general cryptographers. And after that, I want to explain the more technical overview. So if you are not familiar with symmetric key crypto analysis, so please focus on the first 6 slides. Okay, so let's start the talk. Okay, the topic is about AR. Is it okay? Okay, so the topic is about ARX ciphers. So ARX ciphers are one of the design strategy for symmetric key ciphers, and usually, so the ARX ciphers are compared to SBOX-based ciphers like AES. So ARX ciphers, the component modular additions, rotation, and exclusive OR like this picture. So as far as I know, the first ARX cipher is feed at 1987, and there are some successful ciphers, successful ARX ciphers, for example, Chacha and Chasky. And before our session, a new ARX cipher families are proposed, C-Crux and T-Lux. So we have some ARX ciphers, and why ARX ciphers is important. So the reason is ARX ciphers, it has very nice high performance on the software because modular addition, rotation, and XOR is very familiar on any CPU. So the motivation of my talk is the security analysis for ARX cipher is sufficient or not. So of course, we need to compare to SBOX-based ciphers. So as you know, the AES used SBOX. So there are many design papers for SBOX-based cipher, and many attack papers against SBOX-based cipher, and many analysis tools to evaluate the SBOX-based ciphers. But so compared to SBOX-based ciphers, less analysis against ARX ciphers. Of course, some knowledge for SBOX-based cipher is also useful to ARX ciphers, but it's not always. So the ARX cipher is very nice performance. So for example, Chacha is already commonly used in TLS, and Chasky is also standardized by ISO. So I think the motivation is urgent necessity for security analysis for ARX ciphers. But of course, the analyzing ARX cipher is very difficult. So because there are some difficulty of analysis. So one of the reasons is so there is no SBOX. So the only source of nonlinearity is modular addition. But of course, modular addition, only one modular addition is very simple operations. So if we want to attack a few round ARX ciphers, there are very efficient differential and linear characteristics. So usually the target is a few rounds. It's a very easy to attack. But after a few rounds, the security is significantly enhanced. So for example, this is just an image of the security property of ARX ciphers. The first few rounds, the differential probability and the linear squared correlation is very high, so it's very easy to distinguish. But after some rounds, the probability is dramatically worse, and this axis is minus log 2 of p, so the behavior is double exponential. So this example, so that we can attack up to 4 rounds, but it's unlikely to attack 5 rounds because the probability is 2 to the minus 162, so which probability is super low. So as a main focus of our paper is differential linear attack. So differential linear attack is not a new attack techniques, and this attack method was already proposed at 1994. So the idea is combination attack. So first, this is a for of the cipher. The for of cipher is divided into 2 parts. And the first part, we apply differential attack. And the second part, we use linear attack. And in the middle of the cipher, we also magically connect from differential attack to linear attack. So by using the same image, so I said it's unlikely to attack 5 rounds by using traditional differential or linear attacks. But if we use differential linear attack techniques, so by combining 3-round differential characteristics and 3-round linear characteristics, we can attack 6 rounds. And for example, let's see the previous best key recovery attack against Chacha and Chasky. So such best attack comes from the differential linear attacks. So our focus is also differential linear attacks. So this is a summary of contributions. So we propose a new 2 techniques for differential linear attack, and we improve both sides. So we improve the technique for differential part and the linear part, and so we have 2 independent new techniques, and we use both or either. So then we finally lead the best key recovery attack against Chacha and Chasky. Unfortunately, as we can't improve the number of rounds we can attack, but the data and time complexity is significantly reduced. Okay, so from now, I want to explain more technical part. So first, I want to explain what is a differential linear attack. So the cipher is divided into 2 parts. The first part is E1 and second part is E2. So for first part, we apply differential attack. So in this case, the input difference is delta in and output difference is delta m. And the probability satisfying this differential is P. Second step is a linear trade from gamma m to gamma out. And this correlation satisfying this 1-bit approximation is Q. Then in the differential linear attack, we focus on the correlation of these approximations. The left side is an inner product between gamma out and E of x, and right side is an inner product between gamma out and E of x plus delta in. And if the differential probability is P and the linear correlation is Q, then the correlation satisfying this approximation is PQ squared. So, but this is a 1-bit approximations. So to distinguish the real cipher with the ideal ciphers, the required data is P to the minus 2, Q to the minus 4 pairs. So this is the main the main framework of differential linear attack. But when we lead the best attack by using differential linear attack, as a convenient method, use the adding middle round. So this case, the first part and last part is the same as the previous one. So the middle part is added, and this distinguishing is verified experimentally. So we randomly, we choose appropriate delta M and appropriate gamma M. And by changing some delta M and gamma M, and we first find nice experimental differential linear distinguishers. And we experimentally verify the correlation of this distinguisher and let R be the correlation. Then the total correlations for differential linear distinguisher becomes PRQ squared. So of course, this is also one bit approximation. So to observe this correlation, the required data is P to the -2, R to the -2, and Q, times Q to the -4. So in theory, so the differential linear connecting table papers provides nice understanding for the middle layer. But as far as I know, this technique is for SBOX-based cipher. So I'm not sure what happened in ARX cipher. So it's left as open questions. And for my paper, so the middle layer is perfectly verified experimentally. So we propose two new techniques for differential part and linear part. For differential part, we introduce probabilistic independent speeds techniques. And by using these techniques, we can reduce the data complexity from P to the -2, Q to the -4 to P to the -1, Q to the -4. So the gain is P to the -1. And also for linear part, we propose new advanced partitioning techniques with Walsh-Hadamard transform. So the main idea is linear trails, linear characteristics from gamma M to gamma out are dynamically chosen according to the ciphertext. And finally, we use fast Walsh-Hadamard transform to recover the key. So first I want to explain a differential part, but this idea is very simple. So the first step, we find a pair X and X plus delta in satisfying output difference is delta M. So this probability is P. So of course, it's not easy to find such pairs, but by trying out P to the -1 pairs, in average, we can find one such X and X plus delta in. Next, we prepare linear subspace U, where for any U, E1 of X plus U plus E1 of X plus U plus delta in is equal to delta M with probability 1. So this is of course, so this linear subspace U depends on the original text X. But for this X, by adding the linear subspace U, so even if we add some element U from linear subspace, this differential property never change. So if we can find such a linear subspace U, but only by using the pair generated by this subspace U, as a final correlation for differential linear distinguisher becomes Q to the 2. Of course, if we want to use this idea, the condition must be the size of U is larger than Q to the -4. But if this condition holds, the required data is now P to the -1 times Q to the -4. So original distinguisher is P to the -2, Q to the -4. The gain is P to the -1. But of course, the main question is how do we find such linear subspace U? So first, very easy case is a trivial case. So I think it's a very trivial. So I don't think it's so novel, but this case is already very useful. So the part of E1, okay, so the first cipher is divided into 3 parts, E1, EM, and E2. And for E2 and EM, so everything is the same. So now E1 is not full diffusion. In that case, so for example, we have input difference delta in here and output difference is delta M. And other parts, zero difference. And even if we change these values, of course, it doesn't impact on the differential trail from delta into delta M. So this size is M. Then we have a linear subspace U whose dimension is M. For example, Cha-Cha. So the one round Cha-Cha never diffuse each columns. So for example, input difference, original input difference is 0, 0, 0 delta in, and output is 0, 0, 0 delta M. Then these three columns are independent of this differential propagation. So we have three columns that can be chosen from the linear subspace U. So the dimension of U is 96. So thanks to this property, so that we can concentrate the differential linear, experimental differential linear distinguishers from delta M to gamma M. And we can find the half-round extended differential linear distinguishers compared to the previous best one. But the most interesting, more interesting one is a non-trivial case. So we mainly explore the property of modular additions, which could involve full input bits, but it's highly biased. For example, so let's consider the modular additions A plus B plus C. So that if the MSB part of A or B never affect to the LSB part of the output values. And also, even we change the value of the LSB part of the inputs to inputs, so there is a less impact on the MSB of output because so that if we have some impact, the carry must go to the MSB part, but this probability is not so high. So for example, let's focus on Chasqui. So the previous, so we have a 1/2 round differential trail with probability to the -70. And by analyzing this modular addition property, we found 25 bits, which doesn't affect the original differential trail. So the dimension of U is 25. So the next part is a linear part. So this part is much complicated and it's very, very difficult to understand, but I briefly explain the high level overview. So before our proposal, I want to explain the previous techniques, previous partitioning techniques. So now the goal is to compute the ith bit of Z, and from X and Y. But of course, this is the modular addition, so it's a nonlinear operation. So now we first compute P is equal to X plus complement Y. Then we check I-1 bits and I-2 bits of P. So if these two bits are 0, 0, then Zi is always equal to Pi plus Xi-1. And for other case, if this 2-bit value is 1, 0, Zi is always equal to Pi plus Xi-2. Unfortunately, so that this value is 1, 1. This data is not available. But 3/4 data is available with correlation 1. So the previous partitioning techniques paper, so it only used the data satisfying this satisfying 3/4 data. So thanks to by only using such data, so that they can improve the attack. Okay, so now this is our extension. So we first introduce another partitioning techniques, and thanks to this another partitioning techniques, so that we can find a nice strategy where linear trail is dynamically chosen according to ciphertext. And finally, so that our technique used several linear trails, and each linear trail involves different key, but by using Walsh-Hadamard transform technique, we can combine everything efficiently. So first, another partitioning technique. So instead of ith bit of Zi, we focus on Zi plus Zi minus 1, like this. And fortunately, the condition is the bits we need to focus is the same as original one. So it means I minus 1 bit and I minus 2 bit of P. If this bit is a 0, 0, Zi plus Zi minus 1 is equal to Pi plus Xi minus 1 plus Xi minus 2. And for example, it's a 1, 0, Zi plus Zi minus 1 is equal to Pi plus 1. So the important fact is condition, not available condition is different. For example, for Zi, 1, 1 is not available, but this data is available for Zi plus Zi minus 1. And for 0, 1, Zi plus Zi minus 1 is not available, but it's useful for Zi. So why this property is important? So this is a linear trail for modular additions. And so there are two linear trails, blue one and red one. And these correlations are 2 to the minus 1. So it's a absolute correlation is the same. And these two linear trails are best ones. Both are best ones. So after propagating XO and rotation, so let's focus on here. So this bit is a red one. The focus is the 24, but the blue one is the 24, 23. So it means if the data is not available for red one, this data is always available for blue one. So by exploiting these properties, so we check the we introduce 4-bit indicators, and out of 60 data, so 9 data is available. And blue one, also we can use 9 data available, but the available position is a bit different. And finally, we combine everything like this, then 40 over 60 data is available. So for example, the data is 0001. We use this blue linear trail, and 0100, we use red linear trail. So finally, we need to combine so the empirical correlations for each partitions. But it's a bit difficult because if we change a linear trail, the involved secret key bits are also different. So for example, so the sum linear trail involves K3, 23rd bit of K3, but the sum trail doesn't involve it. So usually, if we want to combine everything, we need to additionally guess such key bits. But it's not efficient. So instead of guessing, we use Wald-Shadman transform technique. So the high-level understanding is we first store empirical correlation each partition, and so apply the Wald-Shadman transform. Then we can skip key bits only involved linearly. And of course, we can use fast Wald-Shadman transform to accelerate these operations, so the complexity could be negligible. Okay, so finally, I conclude my talk. So we propose two novel techniques for differential and linear part. For differential part, so the probability, we introduce probabilistic independent bits, and this improves the probability of differential linear distinction. And also for linear parts, thanks to the fast Wald-Shadman transform and the dynamic choice of the linear trail, we can improve the time and the data complexity. But of course, our attack is not perfect. So for example, so our attack technique against 7-round Chachar, so we never use our new technique for linear part because our partitioning technique is super complicated to attack 7-round Chachar. So for 6-round Chachar, it's still simple so that we can attack, but to attack 7-round Chachar, it's very, very complicated. So instead of our technique, we use previous technique called the probabilistic neutral bits technique. But this technique is a black box analysis. So it means that they never exploit the inside modular additions or rotations or XOR. But I think the more theoretical analysis should be better than black box analysis, I hope. So the next question is how to get more number of rounds or to reduce the time and data complexity to attack 7-round Cha-Cha by exploiting the inside of the linear part. Okay, thank you for listening.
Okay, thank you for the talk. So we have time for a question or comment.
Yeah, so for questions, you can add to Zulip. I'm negotiating with Ord Dunkelman right now about whether he has a question or not. Okay, one question from Daniel Bernstein. Any thoughts on the Too Much Crypto paper saying that Cha-Cha 8 is enough? I can repeat it if you like.
Okay. So currently, so it's very difficult to attack Cha-Cha 8. But of course, it's I'm not sure it's enough or not, but I cannot attack 8-round Cha-Cha. This is only my answer.
So it's secure now, but how much time before it becomes attackable, you think? Not to put you on the spot too much. It's okay if you don't want to answer.
I don't know.
Okay. And I think we have, one more question that disappeared. Nope, I think that was it. Okay.
Okay, then I guess we can go back. I mean, if there are more questions, yeah, you can keep posting and answering online. And okay, so before we move to the next social event, please join me in congratulating once more all the speakers. And feel free to unmute yourself, and let's give them a big round of applause. Okay, so Leo